Welcome. Though I have already solved this problem earlier, but uh, someone needs more explanation. Perhaps I have solved this problem in a hurry, and some people are now needing more explanation to solving this problem. So the problem is, first of all, the heading is wrong. Oscillation. This is not an example of oscillation of a plate over a half cylinder. Though I'm going to solve this problem after this, but this is simply oscillation of a bead. And the problem statement is a bead is put on a weightless, non-stretchable, that is what we call inextensible thread, 2L long. The length, the whole length is 2L, I guess. The ends of which are fixed at some height. You can see here, these are fixed at some heights. Under the weight of the bead, the thread sags by a value h. Find the period t of a small oscillation of the bead along the thread. First of all, I don't think it's a question of any rotation, any kind of rotation is involved in this problem. No, not at all. Not at all. Basically, what is involved in this problem is this is a case of a simple pendulum. This is not an example of fixed axis rotation. This is not the case of rolling. So this is simple example of translation. And when a simple pendulum, that means it's a simple pendulum. And when the time period of a simple pendulum, we have several times remember that time period of a simple pendulum is 2 pi under root L by G. So we only need to find out the length of this simple pendulum, nothing else. And you can see here, there are 2 points at the support where this string bead system is fixed. So I can smell an ellipse, because these are the 2 foci, and this bead can move with the length of the string constant, that is equal to 2L. So it will move over an elliptical path. And so I'm going to set up a coordinate system, because it's an example of plane motion. So I'm going to set up a coordinate system, x-axis like this and y-axis like this, with origin at this point. And why I did so, because somehow if the bead came here, just here, so the total length of the string will become this length plus this length, and this total length is going to be 2L, nothing else. If this length is x, this length is also going to be x, no problem. And if this length is y, then you can say here that x plus y is obviously equal to 2L, but because that is nothing but the length of the string itself. And you can write it another way. Suppose you take this length, so this length is x and this length is x, so these 2 lengths are summed up equal to 2x, and this length is nothing but y minus x. 2x plus y minus x is again x plus y, and that will be equal to 2L. So this whole length is 2L. That means this half length is going to be L. this length is L and this length is Y. So you got your ellipse with semi-major axis as L and semi-minor axis as Y. So you can write the equation in a standard, write the equation for ellipse in a standard coordinate system. That will be x upon L square plus Y upon, x square by L square plus Y square upon H square, that is equal to 1. This is the, if we, nothing if, no but. This is the simple equation of ellipse in this coordinate system. And you can do one thing. You can differentiate this relationship. Let's call it equation 1 and differentiate with respect to x. So suppose we are differentiating this relation with respect to x. Then we got here 1 upon L square 2x plus 1 upon H square 2y dy upon dx equal to 0. And this is our equation number 2. And again differentiate it with respect to x. To find d2y upon dx square. So this relation 2, from this relation 2 can be taken out and divided into 0. 0 by 2 is 0. So you got the relation like x upon L square plus y upon H square dy by dx equal to 0. Now you can do one thing. You can differentiate it again with respect to x. So you can write 1 upon L square and dx upon dx becomes 1 plus 1 upon H square and differentiate y into dy by dx. So first differentiate y with respect to x and it will give you dy by dx multiplied by dy by dx. So the first term simply becomes dy by dx, dy upon dx square plus. Now differentiate the second term. Write down y the first term and differentiate the second term and it becomes differentiate. That means we are differentiating dy by dx with respect to x and it comes out d2y upon dx square and that is equal to 0. This is our equation 3. Now if you try to find out this thing, this length, that is the length of the simple pendulum. This length is length of this simple pendulum. Then in order to find this, length, you have to find out the radius of curvature of this curve at this point. And this point is nothing but x coordinate is 0 and y coordinate is minus h. So, and the radius of curvature may be, I don't know, but it must not be equal to minus h. So the radius of curvature of this ellipse at point x equals 0 and y equals minus h. We need to find the radius of curvature of the curve at point 0 comma minus h. If you know the radius of curvature of a curve, so somebody wanted the explanation. If you take the xy plane like this and take a point xy on this curve and draw a tangent here, then you are going to tell me that slope of this tangent will be dy upon dx. And if this tangent makes an angle theta with the positive direction of x-axis, we can write it tan theta also. So that means here at this point P, for a particular angle theta, we can write the relation as dy by dx is equal to tan theta. And this tan theta changes, we know. But if we draw a perpendicular at this point and consider this a small section of this curve as a circle, then if you draw tangents here and draw their perpendiculars, that means normals, they are going to meet here. And this is a small length. This is a very small length. Call it ds. And so if this angle will be simply like very small change in x, that is d theta, very small change in x, and this angle is going to be d theta simply. So the radius thing for this small arc is nothing but if the radii at 2 points, since these 2 points are not separated much, so the length of the normals are going to be the same, and the arc length you are going to write ds equals rho d theta. This arc length is ds, and ds you can write rho d theta. This rho is called the radius of curvature of the curve at a point. So that means we have a kind of thing, rho equals ds upon d theta, and ds you know is a small length over the curve. And if you think in terms of dx and dy, you will know that this angle is theta, because and this length is ds. So if you want to do some manipulation here, you can write rho equals ds upon dx multiplied by dx upon d theta, and dx upon ds is obviously here cos theta, because cos theta equals base by hypotenuse. So cos theta here is going to be dx upon ds. That means sec theta you will get here is ds upon dx. So you can write rho equals dx upon ds is sec theta, and dx by d theta simply. Rho is like this, and with the help of these two equations you try to find out the value of rho. So you got tan theta, and you can find sec theta. I know how, and but you need something else, dx upon d theta. What is this? So I'm going to do one thing. I'm going to differentiate this thing, that was dy upon dx equals tan theta. I'm going to differentiate this once again with respect to x, and so left hand side becomes d2y upon dx square, and this thing sec theta, the differentiation of sec theta with respect to theta is sec square theta. And now I will write here d theta upon dx as well, because I'm differentiating not with respect to theta but with respect to x. So I should write something like that. And so I have equation like d2y upon dx square equals sec square theta multiplied by d theta by dx. Get from here what will be the value of d theta by dx. You know dx by d theta is rho by sec theta. So d theta upon dx from here, d theta upon dx is going to be sec theta divided by rho. So you can write here d theta upon dx equals sec theta upon rho. That means your rho is going to be sec cube theta divided upon d2y upon dx square. And since tan theta is equal to dy upon dx, you can find sec cube theta. So you know sec square theta is going to be 1 plus tan square theta. That means sec theta is equal to 1 upon dy by dx squared, and so sec cube theta is going to be under root 1 plus dy upon dx squared raised to power 3. That means sec cube theta is simply but nothing 1 upon dy upon dx square raised to power 3 by 2, and that you got your radius of curvature of a curve in xy plane simply as sec cube theta. That means 1 plus dy upon dx square raised to 3 by 2 divided upon d2y by dx square. And one more thing, since rho is what was its name, the radius of curvature of a curve at a point, and it's a length, and d2y by dx square can be negative. The terms in denominator, they are not going to be negative anywhere. So for the sake of the fact that this radius of curvature is a length, it's a positive thing, you must put a modulus sign over d2y upon dx square. So that is the radius of curvature of a curve. So formula for radius of curvature of a curve we got here, and that is rho equals 1 plus dy upon dx square raised to 3 by 2 divided by d2y upon dx square modulus. Now you have few things for this problem, these two equations, and you have to find its radius of curvature at this point 0 comma minus h. So put x equals minus h and x equals 0. So if you put x equals 0 in equation 1 and y equals minus h, you will get from this equation that this first term becomes 0 simply. So that means plus 1 by h square multiplied by minus h dy upon dx equal to 0. That means dy by dx is equal to 0. So at 0 comma minus h, dy by dx is equal to 0. Let's try to find the value of dy by dx is 0, no problem at all. So let's try to find out the value of d2y upon dx square at x equals 0. So let's put the same thing, x equals 0, but I don't see an x in equation 3. So let's put y equals minus h. So we got 1 by L square, just making some rough calculations. Well, 1 upon h square, L square plus 1 upon h square. Dy by dx is 0 here, so I'm going to put it equal to 0, and y is minus h. d2y upon dx square equals 0. So that I got 1 upon L square minus 1 upon h d2y by dx square equal to 0. That means d2y upon dx square, that means 1 by h d2y upon dx square is equal to 1 upon L square. That means d2y by dx square here is h upon L square. So at this point our radius of curvature becomes 1 plus 0 square raised to 3 by 2. That will eventually become 0. So sorry. I should erase everything from here and should write here. So 1 plus dy upon dx square is 0 raised to 3 by 2 divided by, what was the value of d2y upon dx square? I just forgot. d2y by dx square is h upon L square. So no problem. I can write here h upon L square, and that was the value of radius of curvature. So value of radius of curvature becomes here L square upon h at that point. So this is the value of the length of the equivalent simple pendulum, and you got the radius of curvature, and in this case time period is going to be 2 pi under root rho by J, that is the length of the equivalent simple pendulum here, and the answer will become simply 2 pi under root rho in place of rho L square by Hg, and that's your answer. Thank you very much for watching or not watching. So